So why does risk-neutral pricing work? How can risky assets be priced as if investors were risk-neutral? And I'm going to review a little bit of utility theory, which goes further than what is discussed in the book, but I think it'll help you understand the appendix and some of the comments made in this chapter. And what we're going to conclude ultimately is that what's called a risk-averse investor, what most of us are, where we want to get paid extra for risk, a risk-averse investor can do all their calculations as if they were risk-neutral, as long as they change their probabilities. So if a risk-averse investor has a certain set of probabilities where they do their calculations and their pricing, there's a way of changing those probabilities so that that investor can make believe that they're risk neutral, and they will get all the same prices that they got using their original assumptions. That's going to be the conclusion of this series of slides on utility theory. So first of all, utility theory provides a mathematical framework for how investors choose between risky alternatives. And risky alternatives can be in the nature of insurance contracts, to buy insurance or not, to invest in asset A versus asset B, to invest in risky asset A instead of a T-bill. There are many, many decisions investors make related to risk. Utility theory provides a framework, a mathematical framework, for understanding those decisions. Each investor is hypothesized to have a utility function, which will denote U of W. It's a function of that investor's wealth. It's always modeled as an increasing function of wealth, and the goal of every investor is to maximize their utility. So intuitively, more is better. Investors want their utility to be as large as possible, and they're making all of their decisions in terms of maximizing, note, expected utility. Because in general, we're making decisions about risky alternatives. So given any initial wealth level, an investor will be indifferent between two risky alternatives or a risky and a risk-free alternative, as long as they provide the same expected utility. So let's see how that's calculated. An expected utility is just, as this expression states, we imagine that R is a random variable in this formula. So U is an explicit function. For example, U might be minus e to the minus x as a simple utility function. And so U is an explicit function. W0 is a dollar amount. And this investor is trying to decide whether he or she wants to invest C dollars in a risky investment. So how does that investor calculate the expected utility of investing C dollars? Well, C dollars from the W is going to go into risky. Now R is a random variable. So when I calculate the expected value of U, the only thing in that formula that's a random variable is the R. So I'm looking at the expected value of R. And on the right-hand side, I'm looking at the expected value of R prime. And this investor will be indifferent between these two risky investments if they provide the same expected utility. That's the theory. That's what it's the underlying idea. So imagine now a risk-free investment over the same period. Well, a risk-free investment has a return which is not a random variable, so its expected utility is just the utility of the return. So an investor will be indifferent between a risky investment and a risk-free investment if the expected utility of the risky investment is equal to the utility of the risk-free investment. RH is the period return. If I wanted to make it an annual return, I might call it HR. But here, R sub H is the actual risk-free period return.